Well, thank you for staying after the first one. Yeah, this is the last talk. And today we had one more talk than yesterday. So if you think that you are more tired, it's not, it's like you have one more talk. It is a physical thing. Well, so now we talk about what were the developments that got us to now be able to map fine structure, to map to do EELS, operando, and so on. But now I'm going to focus in one specific aspect, and this is not exclusive to liquid. I think I add one slide there. I don't know, maybe I will pass it, but solids also have radiolysis. So the thing is that solid, gases, liquid, this is important for any material you put in the electron microscope that is beam sensitive. And as a matter of fact, the radiolysis of liquids and solid is very similar in many aspects. It's only diffusion that then after change a bit. But so I'm talking about solids, and then you're going to see I'm going to be talking also about ice, so like solutions but vitrified, is solid, but liquid. But this is important to many, many, many samples in electron microscopy. And the concepts are the same. Okay. So I'm going directly, if you don't understand why I'm talking about something, because I got a comment that maybe I'm not explaining why things are important very much. So please stop me and ask. Yeah, I have tried to include these things, but now, because right now I'm starting right, I'm going right to the money. I'm talking about radiolysis from slide number 2, because I already said that you can look at liquids and so please stop me and say, okay, why are you doing that? Why do we care? Please. So I can tell you. Okay, so and this is something that we can do now. So that we can look at solid-liquid interface in the electron microscope, and there are different ways of doing it. You can look directly in a liquid. So this is what we saw before. You can encapsulate the liquid with graphene or with silicon nitride with this new polymer thing. But you can also, so this is the most common method actually, you can vitrify your sample, you can freeze it, and then keep it close to native structure, but this is going to be in a solid state, and then look at your sample in a snapshot in time. So this is done in cryo, EM, and so on. So there are these two ways of looking at a solid-liquid interface. Okay, so this is like right to the topic. There is a barrier that I didn't mention very much in my previous talk, but the main problem for this type of technology is that the electron beam actually modify the chemistry. And you want to look at liquids to look at chemical reactions, and you want to look at electrochemistry and so on. So modifying the chemistry, if you don't know if your pH is being stable or if you are changing like your material and so on, this can become a really big problem. You can minimize those, but then you still could have effects that you are not seeing and that are modifying the process that you want to study. So yes, one question that always comes when you are doing liquid cell, maybe outside the community, like is like, but is this like reliable? What? Yeah, and yes, this is the elephant in the room. So for the most part, you show your process and you say, I have done in situ, I have done the same thing ex situ. There is literature that supports it. I do it in cryo EM, and then all these things together say that what I'm seeing is a real thing. So there is a lot of, this is the right way of doing this experiment. You have to correlate with different ways of doing it to show that if this is really is a real process, it's not an artifact that comes from the electron beam. And yes, but because also there is no, we know that sometimes the electron beam can do an effect because you may not trigger the reaction with bias or electric field, and yet you see things happening sometimes. So you say, okay, this is the electron beam that is driving them. But we don't know in many cases because these are complex systems. Your sample every time is different. It was the last question. So every time that you put something in there, it's going to be slightly different, and then there is no data on this that can be adapted to all the cases and so on. So can we uncover electron beam effects in hydrated materials, interfaces, and then once you know something, then usually you can predict it. So can we eventually one day predict these things? Okay, that would be the motivation behind all this. And we are at the very beginning. I don't get too excited that I'm going to give you a model at the end. Yeah, but Okay, so we're going to start with some background on radiation chemistry. So there was a question also in the previous talk, like why you form bubbles. So what is this, all this talking about bubbles here? Yes, so we are going to start with that. And there is a field which is not a field of electron microscopy. They work in many things. They are trying to clean nuclear reactors. So they use radiation to decompose molecules. And this is like what they do in radiation chemistry. They clean water using radiation, different radiations. They clean nuclear waste. They do cancer therapies now. There is like a way the flash radiotherapy. There are things like that that you can do with different radiations. And this is what actually we do in the electron microscope. We have electrons. This is on top of that, they are ionizing radiation, and when they go through matter, they are producing chemical species. And this is a model, it's an old model for the solvated electron. This is one specific species that you can have when you are irradiating with radiolysis. Usually you don't have electrons going around like this, but in radiolysis you could have a solvated electron, which is an electron that is going to be stable for a very short period of time, but it's going to be stable in solution. Okay? And if you have, so some of the basics is that, well, if you have a diluted solution, okay, and they gave this number in radiation chemistry, it was Jacqueline Belloni in Paris, less than 0.1 molar in your concentration, then you can assume, because these are not very selective processes, you have your liquid, you start irradiating in your microscope to study anything that you want to do in a liquid, and then this is not very selective, you're going to start irradiating relative to the relative abundance of molecules that you have there. So if it is very diluted, then you need to worry only about the solvent. And then this simplifies things a lot, because it's like, okay, if I know what happened to water, then I know what is the chemical changes that are there, even if I have something else in the solution. But this is going to be affected by these radicals. But yeah. So this is something important. It's because it's a matter of statistics. So if it is very, very diluted, you could focus on solvent only, and then you know what is going on. So this is, so radiation chemists, what they do is that they do this type of diagrams. So, and this is knowledge that has been built for decades. So yeah, since the 30s, and then you have water, you irradiate it with X-rays or gamma rays with electrons, and what you see is that you ionize your molecules, and this happens really, really fast in the femtosecond time scale. You can also produce excited electronic states of water really quick, and then there is all these decomposition processes, so then you leave it alone, and these molecules are going to interact, they are going to recombine, and there is all these processes. This is simplified, so they are not here written, it's only a picosecond, these are the species that you have, microsecond, the species that you have, but they know what is going on in between and what is the amount of these species that you are creating. So they know that. The amount of species is something that is called a G-value, so it gives you, at the end, in the picosecond, they have it tabulated, so you have this many species every 100 electron volt that you put, that much of the hydrogen atom, that much of the, so they know these things. This is something that is well studied in radiation chemistry. And I don't want anybody to get like scared already, but yes. So we are gonna see like how this happens. So what happens is that this doesn't happen in an homogeneous way. It's not that you start irradiating your solution and you break things homogeneously everywhere. So this happens in a small pockets of chemistry along the electron track. And so this Monte Carlo, I think Sophie was showing that when she talked about the phonons, all these Monte Carlo tracks of the electrons producing secondaries and so on. Along this track, you're going to have these pockets of chemistry, which are going to be really sparse that happen, and each of them is different in reality. But the way that you handle this, because it's really complex, is by averaging things. So it was like in DFT, when we were talking about the effective potential, things like that. This is really complex, so what you do is that you look at some average sparse, which has an average size, something between 2 and 10 nanometers. It has a chemistry that is the average of all these pockets, and then with this, you can model what is happening. So it's a mixture between stochastic of how many of these things you are creating, but then also deterministic in the term that you say, okay, my sparse is going to have this chemistry, like if it was something homogeneous, everywhere, this chemistry, and then it's going to have this size and it's going to diffuse and so on. So yeah. Yeah, so this is just a snapshot of electrons going here and then different things that are going to be producing these spars. And then it is assumed that for electrons, these are well separated. They don't interact with each other. And there is an average chemistry that they use for this. Okay. And then there are two different types of radiation. If you go to the, see, yes.
How do you have the evidence of the formation of these pockets, and which size have these pockets, and can you control them in some way?
Yeah, I don't know how they do it, because these are radiation chemists that do this. I know that now, but this is known for a long time, so I'm sure it's not measured in the way that I'm going to say. So I don't know. But right now there is ultra-fast techniques to looking at this more in detail. But yes, I don't know how they came out with this thing experimentally before. They probably
the
use...
microscope seems the right tool to observe these pockets in some way, you know?
What, Mike?
With a microscope, with some sort of a spectroscopic imaging, maybe it would be feasible.
This is really fast. Eh? This is what happens at the, close to picosecond. Yeah, this is... Okay, so if you... Yeah, I don't know, but it could be, yeah. They could be using like tricks, like scavengers and things like that, like so indirect measurements. But the truth is that I don't know, but I just know what they learn from all those experiments, a little bit. Okay, so there are two different types of radiation when it comes to this behavior. One is called low linear energy transfer radiation, and those are electrons. So electrons, what they do is this. So they create these pockets of chemistry, and they are very well separated along the electron track. If you go to the synchrotron and work with X-rays, this is very different. This is high linear energy transfer radiation. So the behavior that it has is like this. So you really create a lot of chemistry along this track. And these things do interact, but they are very close to each other. And then if you want to express this in some kind of average chemistry, you don't talk about the spars, you talk about something that is like a blob, they call it, and it's bigger because of this interaction. So they are very, very close. So in case you don't know, this is a parenthesis here, X-rays are much more damaging than electrons. It's just that the doses that we use in the synchrotron are lower. And the reason for that is this. This is why they are more damaging. You're transferring much more energy to your material than an electron does. Okay, so this is usually the two different things that we have. And I'm going to be focusing on electrons. So in principle, we should have this. Yeah, and the comparison between one and the other in terms of the chemistry that you produce at the end of the day is that because you're going to have more interactions, then you have more and more recombinations. And what they have seen in radiation chemistry is that this leads to more molecular species instead of radicals. So there is a difference in the chemistry that you are producing, is more molecules. Okay, so now I told you this, and now I'm going to go back again to the diagram to go back again to this process. So what we saw of the spars, so you have the water, you irradiate with your electrons, and then you're going to create ionization of the molecules. So you're going to separate by charge, and then you have excitation of the molecules and different processes that come into play later on. And this is the time scale of this. So the excitation, yes, so, and this is the chemistry, is a drawing of how the chemistry is in your sample. So you start with something that is really inhomogeneous, all these pockets of chemistry, all of them different, even though we describe them as like something homogeneous, but all of them are different. Then they start diffusing at these recombinations. So all this is when they diffuse. So the chemistry inside the pocket starts changing over time as these things diffuse away. And then eventually, so this, when you arrive to the microsecond time scale, then eventually you are going to reach an equilibrium. And that's when your chemistry starts being homogeneous in the solution. So you go from something that is inhomogeneous, like these blobs like this, and then, I shouldn't say blobs because that's for X-rays, but then all these sparse diffusing, and then you end up with something that is homogeneous after the microsecond time scale. And this is, yes, you have a question.
After 1 microsecond, you have this collection of species, right? But suppose that you wait for 1 millisecond. It's going to recombine to the initial state of the species?
Well, the time is not, so it's in the microsecond time scale. So there is people doing more, but so I don't, it's not going to be 1 microsecond, but yes, in the microsecond time scale, you are going to have these species, and then a radiation chemist is going to tell you how much of each of them you're going to have in proportion, depending on the electrons you have put. But then if you leave it alone and you don't irradiate, you go back to water. Yes, they start like this, and then you end up having the initial water. And this is important for this slide because, yeah, what happens is that usually you don't study only water, you have something else. And then the moment that you have something else in your solution, this thing is going to go into a complete different direction. And this is when you have additives. So in radiation chemistry, they add additives here. And yes, this go into some stable products. So if you have a precursor, and then there is like silver nitride, there is like all these things that we have grown in the microscope and they have grown outside. If you have something that is going to react with this species, then you can grow particles. And these are many experiments in the electron microscope where you grow particles, different type of particles, because you have a precursor there. And then you can change the chemistry in many different ways. So how much can you change your chemistry? Because you're using electrons. So, well, this was a paper where we demonstrated for the first time that you could increase the pH. So usually, until then, if you just have water and then you irradiate and you do modeling, what it tells you is that you are always going to decrease your pH. This is what you do. But we put cerium species here. We were doing a specific experiment. And what we saw is that we went from having a solution of cerium 3+ as an initial solution, and we ended up having this hexagonal phase. We didn't end up with the cubic phase that we were aiming for. We ended up with the hexagonal phase. And the only way to do this is by increasing your pH. So this was the first time that we demonstrated that you can go in like any direction, really. So you can oxidize things in your microscope because of the effect of the electron beam, or you can reduce things. And one would say, like, oh, I'm using electrons, I'm just going to reduce things. No, you can oxidize things, and these things are in competition. So here we increase the pH, and I also proposed this Pourbet diagram at the time. They have not been used much, but this is really nice because then you have all the species that you have, and the redox species, and in which direction things are going to go. So for interpretation of results, it's very helpful. But well, it is like there. One day it will be used. Okay, so this is like how to think about this. You have your solution, you are creating this primary species, and then you can add something, and then you can change the environment. And the way to think about it is with reactivity. So you have this kinetic constant that is like how fast they are going to react with this species. So if you have, and these are the main from all this pool of species that you have after the microsecond time scale, so in your homogeneous regime. These are the main three, so the most abundant and also the most reactive of them. So the aqueous electron, the solvated electrons, the hydrogen atom, and then the hydroxyl, the hydrogen radical and the hydroxyl radical. So these are the main three primary species of the decomposition of water that you are going to have in your solution. So if instead of having water, you add some of these things, then you're going to have a certain reactivity with them. So for instance, you can add a nitro group, and this is going to react really effectively with aqueous electron and also quite a lot with the hydrogen atom, and it's going to leave your OH alone. So what do you think is going to happen if you do that? what you are going to end up is having only OH or mostly OH, which is an oxidizing environment. So you could do oxidation if you do something like that. This is like the use of scavengers that they do in radiolysis. So if instead of that you add an alcohol, a little bit of alcohol in your solution, yeah, it's going to leave alone the aqueous electrons. It's going to react quite a lot with the hydrogen atom, and then it's going to react a lot with the hydroxyl radical. So you're going to end up having mostly a reducing environment in your microscope. And this is how you can change the chemistry that you have for experiment. And this is the first paper using something like that. It was in 2014 in collaboration with some radiation chemist in the paper. And this is from Katie Jung-Johan and then Ellis Sutter. And what they did was actually adding alcohol in the solution. And they could go from a growth of particles, usually, I don't remember which particles, but you need to reduce them to grow these particles. I don't remember which particles. But you go from something that, yes, you are growing them, but you can see the effect of competing reactions because this is not an homogeneous growth. There is something that is also trying to dissolve them simultaneously. So you go from something like that. This, you are growing it with the electron beam. So you just have a precursor solution, so water with your precursor, and then you start irradiating and you grow particles in situ in the microscope. And then this happens because of the reducing agents, but then you can see the effect of the oxidizing agents in that they are also trying to dissolve your particles at the same time. You add an alcohol and then these become much nicer. So like you have something that just grows and you get rid of all these competing reactions that are trying to dissolve your particles simultaneously. Okay, so this was the first, it was a proof of concept paper of that you can do this in the microscope. We do have like some of the things in radiation chemistry we can apply because we use electrons, so yeah. Okay, and then we published this review in 2017 when we put a lot of this knowledge from the radiation chemistry for people to use, and we did a table where we said like everything that we could find, on if you mix water and then you saturate it with this, and then you have this pH, you're going to end up with this, which is a single radical oxidation. And then if you add terbutanol, this is a big one, you're going to end up only with aqueous electron, which means that you have a single radical reduction. You only have electrons there, so you know what is going to happen. And like this, you can control things. And then you can go even further because we added this column here, and these are the redox couples. You can change the redox potential too. So you see you have water in all the cases, and then you can choose like what is the solute that you are going to add in here for doing your scavenging, not just to have oxidizing or reducing conditions, but also to choose the redox potential that to be much more aggressive or to be much more mild. So that you want to have, and this could be helpful if you want to match some specific reductant or some specific oxidizing agent that you're doing outside the microscope. And I'm going to select one, but yeah, okay. So yeah, this is an example. So not everything is water, and you can also use these holders with something else. Yeah, in this case, I used toluene, and something that is important if one day you want to use this table is that you need to control the oxygen because oxygen is also a scavenger in many cases. Like all these numbers that they give in radiation chemistry is assuming that you are controlling your environment. Otherwise, they would put add oxygen. But usually we do the loading and there is oxygen in there and this has to be taken into account, or you need to buy a glove box for aqueous solution for the oxygen. Yeah. So this was done in a glove box, controlling the oxygen. We did and these are very sensitive, this growth of particles. They were doing this in the synchrotron and they wanted to do it also in the electron microscope, and we have to put really high doses because these are, the scale is 3 nanometers. You have something growing here and then popping out and then another particle and so on. And it happens really fast because these were still very thick layers of liquid, and we wanted to see like really small particles that would then be stable, so they don't grow more than this. They grow all the way up to 3 nanometers. Yeah. Okay. So if you use other solvents, so they have different properties, and this was just to show, it was like the first time that we used an aromatic hydrocarbon to say that if these are very stable materials, so you could have a production of radicals that is much lower. So you can slow things out a lot. So the aqueous electrons formed, if you are using water as a solvent, is 2.7 molecules per 100 electron volts in the typical conditions of radiation chemistry, microsecond time scale, equilibrium, and so on. If you use toluene, this goes down to just 0.14 molecules per 100 electron volts. So this is a much nicer environment. It's going to allow you to do an experiment for much longer. The tolerance is much higher. And also, if you control your oxygen, you are going to be doing your reduction only with molecular hydrogen. And the redox potential of molecular hydrogen is close to 0. And this is very similar to ethanol, isopropanol, anything that you are doing outside the microscope. So I did a figure. This got rejected many times. I did a figure where I was comparing directly the data from the synchrotron from what we did in the electron microscope, because I said, you see, you have the redox potential is similar. And a reviewer came back and he said, you cannot be possibly serious doing this comparison with the microscope. But yes, the dose rates are different, but your reducing agent has similar properties when it comes to reduction, because it's similar redox potential. Okay. So, but for doing this, you need to do the solution in a glove box, transfer in oxygen-free conditions, doing the loading in oxygen-free conditions. You have 2 hours before you start getting oxygen and all these like agglomerates, and put it in the microscope. So they are not easy experiments, but okay. So these were some concepts of radiolysis. So now, if you do this in the electron microscope, how different is this? So what are the things that are not really the same that all these things that are tabulated and that there is all this information about? Well, the first is the dose rates that we are using. And here I'm doing a comparison. So if you, all this data that from the radiolysis of water and from other materials has been done with, so the typical gamma radiolysis, these are accelerators that they use, and they use a magnitude, oh, okay, I didn't put this. They use something called gray per second, this is real dose. We use electrons per nanometer or electron per nanometers per second. And this is a fluence, it's not really a dose. We call it dose in the electron microscope, but it's not a dose because it doesn't take into account the absorption of the material. But yeah, I didn't put the equation, sorry. Yeah, but well, I did the calculation. So you are exposing the water. Here I did the calculation from our electron flux in the microscope, and then assuming the thickness and so on. So at the proof, if everything were absorbed, which is not the case because it's a thin film, you would have 10 to the 15 grays per second to do my EELS. Okay, the condition that I have for EELS is 10 to the 15 grays per second. While in gamma radiolysis, they use 2 grays per second. In a nuclear reactor, we are talking about 1 kilogray per second. In an industrial electron accelerator, is 100 kilograys per second. Yeah, you threw a bomb into this material and it's still lower. So in the middle of a nuclear explosion, there was a paper that I don't remember from the 80s where they did the calculation, and that was lower than what we have in the electron microscope. Okay, so and they get really surprised, radiation chemists, when they see the numbers. Yes.
Have you done this with the trim calculations to sort of get an estimate of what fraction of that actually would be absorbed by the water?
No, we will do it, but yes, it is true. You don't absorb. This is in the SEM, really. If you have the same condition in an SEM, because then you will have everything, your whole radiation volumes in the sample. But yes, in transmission, you don't have all this absorption of energy. This is why I said that proof here
I mean,
because
it's only
it's
going to
heating,
reduce it by
heating.
like a few orders of magnitude. It's not going to reduce it by like 15.
Yeah, yeah, it is lower than this, and it's going to be much lower than this. But well, this has to be calculated. We haven't done it, but yeah. Okay. But yeah, this is like the rough estimate what you would if you just take our electron flux and translate it. But this would be how many electrons we are putting in there. But it's not really like the absorption that it's going to have. Okay, so I'm going back to this. I show you this from radiation chemistry, and we have fast electrons doing this, and then you have X-rays, and they do like much more damage. But now we know that we don't have really this, we have this, but we have plenty of them. So we did a paper recently where we wanted to show experimentally that where we are, in the conditions that we are, is closer to a scenario like this. And this means that, yes, you have electrons, the physics are the same, so we still are doing the same electrons that they use in radiation chemistry, but we have many of them, and they're really close. So what this could be doing is that all these pockets or these spars could be interacting with each other. And this is an idea that has been in the community for a while. We wanted to prove it experimentally, and I'm going to show like 2 experiments in different time scales that we are looking at this. But yes, the first time I saw it was 2017 in a pre-meeting congress in M&M with Jay Laverne, so basically this figure. And yes, what we could have is at very high fluxes, we could have this interaction, and then we would be closer to conditions of X-rays than actually electrons. And then the chemistry is going to be different from what we have assumed from electrons.
How do you detect interaction?
Now that I think I know. Yeah, I still don't do this thing, but you look at the outcome. So they know that how X-ray, you can change the linear energy transfer radiation. So you do you compare if you have the same thing, and then you say, okay, this thing is behaving more like this, and then, well, this is a way of doing it. This is the way that we are doing it because we are looking at the product. Yes.
These conditions are just adequate in homogeneous phase or also in heterogeneous phase?
We are talking about the sparse. This is heterogeneous.
Heterogeneous?
Yeah, we are still in the fast regimes. And this is very important because in that diagram, all the models that there is in place, so in liquid electron microscopy, we use models, and everything starts from the microsecond time scale, which means that you are taking the G values that are tabulated and so on. So the whole point of this paper here was also to say that the G values that we are using for models and so on, because these faster, like the previous stages are probably different from what we think, they're probably not right. So we shouldn't take them directly from radiation chemistry, we should like revisit them.
Okay, thank you.
But yes, right now we are in the non-homogeneous, like in this slide. Yeah. Okay, so back to here. So first difference was the electron fluxes that we are using. They are really high compared to what they use in radiation chemistry. Another difference is that we don't really want to look at bulk liquids as they do. We care about interfaces because we are using electron microscopy, we want to do EELS, and then, we want to look at things that are nanoparticles at the surface or they're going to be encapsulated in membranes. So we always have interfaces in these experiments. And this is going to change things. So when you have a solid, this diagram, all these kinetics and then the production of this species is going to change. And it's not only at the end, it's like it can change all along the decomposition of the molecule. So this could change things. And it's not very well understood because they don't do a lot of work on interfaces in radiation chemistry, how this is going to happen. You could have catalytic effects. And so all these things are not taken into account in radiation chemistry. Well, there are some works, but not many. And unfortunately, the effect of interfaces when you are doing experiments with liquids in the microscope is really, really high. So every time that you are doing growth of particles, you are going to see that at interfaces. So this, that I showed this, I don't know if I saw before, no, I didn't. But okay, this is from a paper where I was comparing the effect of primary energy and some other beam parameters with silver nitride. And then here you have two planes. So you see the particles in this, that they are in focus, so this is on the top membrane. But then you see that there is like all these blobs here, all these are particles that are on the bottom membrane. And you don't have things in between. So you have this plane, and this is where the nucleation and growth happens. So there is an effect of interfaces. This one is even more important. So this is not water. I think this was methanol, yeah? And you are looking at carbon on gold nanoparticles, and then you see that nothing happened here in the solution, but this is only irradiating with the electron beam. So you have this solution where you have gold nanoparticles, copper dissolved in your solution. You start irradiating and you see growth, like almost looking like dendrites, what you would do if you were, you know, like doing electrochemistry almost. And you see that this growth on the surface and then it dissolves. So you can change your settings in the microscope, you can grow this thing, you can dissolve it, you can grow it just by changing the parameters. And this happens only at interfaces, it doesn't happen in the solution. So the effect of interfaces is really important. And we don't understand it, okay? And when I said that in radiation chemistry there is not much about this, I mean, there are some things. So this is one example. This is a work or slurries, silicon slurries. So they were looking at silicon in still bulk. So you have a solution with nanoparticles of silicon, and then they were changing the content of water to see how radiolysis changed. So if you have 100% water, so this is like the reference value. If you have the radiolysis of water, you are going to create, this is the G value for molecular hydrogen, which is the species that they use to compare these things to know what is going on. So yes, you can compare the value of how much hydrogen you are producing in just water, and then you start adding these particles, and then you see how things change, and it always increase, and you have like amorphous silicon nitride, silicon dioxide, silicon carbide, and alpha phase silicon nitride. It always increase if you have this, but then, this is something that is quite interesting, there is like this inhomogeneity there. So when you have just a little bit of water, this radiolysis gets like, you produce a lot of hydrogen in comparison. So this is like quite interesting, because then you have, I don't know, some of the graphene cells that you have like just a bit of water. There are experiments with vapor water. So things change a lot at these interfaces. And it increases actually here. So there is some information, but it's still bulk. And yeah, okay. So how can we use EELS to help with this? And this is at the beginning, so it's not, yeah. But I already showed you this, so we can use EELS to study these processes because it's such a broadband technique that is going to give us information along all these diagrams, if the cross-section is large enough for it. It's not that, yeah. So we could get information of excited electronic states. You can get information of the species. This is molecular oxygen in liquid water. In this same paper, they show this peak coming in and out, and if you are producing this species, yeah, and you can go so from the physical processes to the chemical processes. Average, because I don't have ultra-fast microscope, but still you can look at this. Okay, so what we did, and now this is a bit tricky because I'm going to talk about ice. So I have been talking about liquids, and now I'm going to show you results in ice, because what we wanted was a freestanding layer of water without interfaces to start with. And then what we did was like freeze the water and do the cryo experiment. So this is cryo EELS, it's not liquid. And I will talk a little bit after of what happened with solid liquids and what happened when you change temperature. But yes, so what we did was like, well, so what we saw is that all these pre-peaks that are in front of the oxygen KH of water are actually information, because they tell you about molecular species. So this is the peroxide, this is this peak, yeah. So the peroxide, molecular oxygen, and then you have the OH radical, oxygen radical, and so on. So basically you have all the species that you can create with radiolysis, except for molecular hydrogen and the hydrogen atom in water. Yes, and these are like radicals, and then the pi peak and the sigma peak. And the first thing that we saw is that for the most part, we have a huge amount of molecular oxygen as compared to peroxide, for instance. Like this is like quite, because usually you should have more hydrogen chemistry than oxygen in radiation chemistry. You should have more peroxide. And molecular oxygen is not one of the primary products, it's a secondary product. So you should have less, and you have a lot of it, okay? Yes, so this is already different. And what we did was comparing this with X-rays in the synchrotron, or the data that published by the group of Lafont here, NEXAPS, so we can do this comparison. And then you have, so they have data at 20 Kelvin, similar conditions. We are in both cases talking about 60 nanometer. Probably mine was thicker because I used the normal methods for the thickness. But anyway, yes, 60 nanometer water films, and then 90 Kelvin, 96 Kelvin for some of the measurement. EELS was 96. There is a nexus of 90 Kelvin, a huge difference between the energy that we introduced, but well, and then what we see is that this is still different. So we do have more production of molecular species, and this goes in the direction of having more secondary process or more recombination, being closer to X-rays, but yet the chemistry that we see for ice is slightly different. So and this will require like modeling to really understand. And then, okay, I'm going to do a parenthesis here of why I'm talking about solids when I want to study liquids. And the reason is that something that we were discussing in the paper is that, well, if you compare the low loss regime from different materials, is this really similar, and most processes occur in this energy range. They're exclusively low energy. And there is very little that is not, but in radiation chemistry, they always assume that solid and liquid behave in a very similar way. If you measure a gas, it's going to be very different. So you can compare ice water, liquid water, and then water vapor. The low energy spectra, the dipole oscillator strength is going to be very similar, and then for gas water is going to be quite different. So in principle, we were assuming that we could do this to a certain extent. And because it's ice, and you are changing also the temperature, then there is something else that you have to take into account. So until the picosecond time scale, it is assumed that these G values, so this is the production that they have measured in radiation chemistry for picosecond yields, it should be the same. And what we see is that, well, there is no or little molecular oxygen. This is a secondary product, so it is not here. And then from here, there is diffusion kinetics. There is all these spars and the way they are going to diffuse, and this is going to change with temperature. So we are looking at, so the following kinetics from here. This is what we were trying. Okay, so what I'm doing now is that I'm trying to explain the results. Okay, this is not background. we were thinking like, what is going on? Why things are different? Okay, so so we were thinking it should be the same all the way till here, according to radiation chemistry. But then from here, the diffusion kinetics are going to be different because we are at different temperatures. And if you look at the mobility of these species, you have that the hydrogen atom and aqueous electrons are going to be mobile. They're not going to care if you go to 95 Kelvin as compared to room temperature. So this is more or less the same. The OH was a tricky one because depending on the paper, they're going to see that it's not mobile at 130 Kelvin, or it is, or it's not clear. But it is going to be partially mobile because, so what we believe is that depending on the technique that you use to measure this, you're going to detect it or not. So it should be mobile for some people to measure it at 130 Kelvin. So it's going to partially diffuse. It's probably going to go slower. But then heavier molecular products like the peroxides and the HO2, O2, hydrogen, they shouldn't be mobile. So you go to 96 Kelvin with a cryo holder, and these things should not move. So you're going to be changing that. But we keep thinking on how to explain this, okay? So if you think about it, you say, okay, maybe it's the temperature. The problem is that if you have limited diffusion of some of the radicals and of the molecular species, you should have less recombination. So usually you would expect less molecular species. So this also doesn't really explain the results very well. Yes, and with this experiment, so each of these points is an area like this, when I am averaging like the spectra. And we did like different systematic studies, different parameters to see, and we were tracking the production of molecular oxygen. So some of the things that we saw is that molecular oxygen and that peak from the hydroxide goes in opposite direction always. So this, what it means is that you are converting one into the other one and vice versa, so they are linked. And also, well, these are like, I didn't put, okay, no. I don't know how many of these I put. I think it is not much. 1 second. Yes, it's not much. Okay, so I just selected 2 results. So this one is the beam separation. So this is really interesting because you have a 2 Armstrong beam and you do a leapfrog scanning because I don't have a lot of signal and I want to have an EELS spectrum with not much noise. So to increase my signal to background noise, what I do is the average of many spectrum. But for that, I separate my points and then we look at what is the production of oxygen and OH. And what we see is that we keep increasing. So these points see each other for 10 nanometers, 20 nanometers, you change to 30 nanometers and this keeps changing. So in the same conditions of irradiation, if you change the separation of a 2 Armstrong beam and you separate it 20 nanometers, they still see each other. So because you keep separating and you keep changing the values of production in fresh new areas. Okay, you repeat this experiment in another area fresh, and I measure the thickness, so this is comparable. And you have to go all the way to 70 nanometers separation, 80 nanometers for these things to not see each other in these specific radiation conditions. It could be different. But so, yeah, you see that there is some diffusion, some kind of effect that where these things see each other in the core loss. We are not in the low loss, so this means that it's a real thing of things diffusing away and interacting with something that is happening nearby. And you have to go really far away, like 70 nanometers for this thing to not happen. And then we also look at the effect of those. Yeah, and we have started this, we are still working on this, but we are looking at interfaces and comparing just water with different interfaces. And this is the last thing I'm going to tell you about this. What we did was proposing a model of how oxygen could be produced. So what are the equations that could come into play to actually produce molecular oxygen? And if you look, so we're not going to go through this, but you see that there is a lot of recombination of radicals for this to happen. So the OH has to recombine with itself and the hydrogen atom as well, and then and to end up having molecular oxygen, which means that we are in this condition where everything is happening really, 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 really fast to end up just with molecules. Okay, so that's where we are. We have a tons of data to analyze, but yeah, that's where we are, like how you can use EELS to look at production of these species and then try to understand. Then you need to combine this with modeling. And yeah, okay, so the last thing that I'm going to show is like how to use EELS to look at these processes, but in a much faster time scale. So now we are going to go to the beginning of the decomposition of molecules. So, yes.
It is like, for instance, you could go maybe 2 slides back. Well, maybe the next one is good enough, right? Next one.
Next one.
Yeah, this one. So here you have all these different processes of the thing that they could occur, and then you are doing this with the core loss, right?
With what?
With core loss. Like when you measure, yeah, when you measure the things. So when we were looking at Raman with, I'm sorry, like the papers of the isotope with the water, or heavy water with Jordan,
Yes.
then we saw that there is, like, superficially searching that, for instance, they do Raman spectroscopy, and depends upon the shape of the OH, they can say which radicals you will have in water. So I'm wondering if you will be like having since the cross sections are similar for core loss than for the phonons and the OH, you will be able to really see which of the processes that occur will be able to be observed by looking at the OH signal on the phonons, on the molecular vibrations of water, like at 300 or 400 millielectron volts.
Not me.
No, you, like in general, like
Yes. And
because in Raman they go and they see, okay, this is whether
if
it's going to
they
be
can
like
do
that.
it in Raman, I guess yes. Right?
Because all these experiments that you're doing, probably they will be, but then the problem is you have the encapsulation. Mhm. Okay.
The problem with doing this with the water OH stretch is that your water vibrational OH stretch peak is dominated by the H-bond network inside the water. So basically, all the different water molecules aren't just vibrating independently of each other. They actually see the surrounding water molecules, and the frequency of the OH stretch is actually dominated by that interaction between the neighboring water molecules. So dynamics in water will disrupt the hydrogen bond network, but you really need that extra level. I would predict, I don't actually know enough about the Raman to say how they account for that, but I would predict this would be that difference between sub-milli-electron volt energy resolution that you get with Raman spectroscopy and the 4 to 5 to 6 milli-electron volt energy resolution that we get with EELS, is the ability to distinguish between normal OH stretching in the H bond network and these types of radicals.
Okay. And if you could change the whole network so that the most thing that you see is damage, then you would. Yeah. But then you have to like assume that the in between is. Yeah. But yes, what you're saying, you need more energy resolution to see the two at the same time. No, both. Yeah. Okay. But yeah, I don't have the energy resolution to anymore. But I don't know. I could go like somewhere. Yeah. Okay. So now we are gonna go to radiation physics. That was radiation chemistry. So how EELS can help with radiation chemistry. So now for radiation physics and physicochemistry, and this is the last part, really. Okay. And just gonna show you one result. So, okay, but first I need to explain you what we are going to look at. So this is another type of diagram. So before we saw, so for the case of water, this diagram that I show you, now I'm going to explain you a little bit the difference between, without going into these things, like the diagram that I show you for water and what happened with a cyclid hydrocarbon. So this is a different molecule, right? So if you have water, 98–95% of the decomposition is going to come from ionization, and all this comes from the dielectric constant, the properties of water. So your excited electronic states are going to, basically like go back. But in hydrocarbons, this is the opposite. So what you have is that you are going to produce ionization, but then there is very fast recombinations of the charges, and this is also because of your dielectric constant. They have something called the Onsager radius to look at these different type of behavior. So what is going to happen is that they're going to recombine, and you are going to end up with most of the damage, and in a similar ratio, so like the 95%, 90-something%, is going to come from excited electronic states and not from ionization. So these are two different things. And okay, so it's a bit different. And then the way electrons excite these things, so if you're doing optical spectroscopy, you give a specific energy, and then you go to the first excited electronic state, you do 2 photons, and then you go to the second excited electronic state, and so on. So you do second harmonic, and that. But what we are doing with electrons is that you are populating, and this is also what Sophie, I think, I'm not sure, but I think this is also like what she was showing. But yeah, so what you do is that you populate the higher excited electronic state in this decomposition, and this is going to go down to the first excited electronic states. And then there are different pathways to this. Either it's going to go back to the ground state, or it's going to produce damage. So usually it's the S1 and the T1 that are going to be producing radicals and molecules. Yes, so this is like what can happen, like either this or this. And this is what, yeah. But there is not this idea of giving an energy going here, giving a higher energy and then go here, and so on. This is in this other way around. You have the higher excited electron until the continuous, and then it goes down. And the consequences of that, when you are doing spectroscopy, is that you have access to all the excited electronic states at once with electrons. You can see the single excited electronic state here. So this is optical. This is why I put S1, S2, S0 to S1. But in this case, this is just S1. Okay, you have the first excited electronic state here, second excited electronic state here, and then higher states. And there are solids here, and there are liquids, and so on. Okay, and just to mention that if you have enough energy resolution, and from all these spectra, now I'm looking at liquids with the microscope that I have, which is also monochromatic. We can go down to 70 milli-electron volt. It's just that I don't have enough time in the microscope to do this every time. We are struggling for time. Yeah. But in super STEM, where I was before, I was looking at solids, so drop casted rhodamine and also electrospray rhodamine in carbon, where there are some differences. And this noisy spectra here has even more information because you have much higher energy resolution. At the time, it was something from 15 to 35 milli-electron volts or so. And with that type of energy resolution, you can see fine structure. And this is vibronic states within the excited electronic states. This is a side thing. Okay, so I'm just going to show you the last result. So with EELS, I have shown you this before. You can look at these excited electronic states in liquids using this type of holders. And you can get your rhodamine with water if you do this 60-40%. We also saw that before. And then what I see is this. So this is like our main result. This is the measurement that you do without any irradiation. And you have two channels. And if you go from A, you irradiate this area to E. And I'm subtracting the reference from the silicon nitride in between for the zero loss. Then what you see is that you start with your first excited electronic state. This goes down with the scan direction, and higher excited electronic states go up. And you see it here as well. So all these are like different areas coming from this side to this side of the channel. And you have this one that goes down, and then some peaks that come later on in this channel. So this is something very strange, okay? I was expecting to have an average of everything that I can put together, so this is less noisy, and what you see is that there are differences along the scan. Yeah. And then this happens in every channel that you go. That you have to have a large enough area for seeing this. If it is small, but you only stay at the beginning, so you don't really see it. But here is the same. If you compare this area here with the one at the end, so this is area A and area B here, and then you compare the first scan in a cumulative dose series with your last scan. So here I have been trying to damage these things in water because that was the original purpose of these experiments. Then what you see is that first, they don't really care. So this is like, you can irradiate a lot and maybe it's going to decrease and then it goes back. So you don't really damage these things very much with cumulative dose, just, yeah. But if you compare in both, like the beginning and also at the end, the area A with the B, so this area here with here, you see this goes down and this go up. So, and there is a decrease of water with those, so this part here in the, so there are things happening to the solution, not to the rhodamine, not very much, with cumulative dose, but if you compare these two parts of the scan, then you do see differences. And I think this is my last. Yeah. Okay. Hold on. This is just last slide. Okay. So now we're going to try to explain what is this. Okay. So if we go back to this, and now I have like add some more steps. Usually, damage is believed to come from the single excited electronic states and triple excited electronic states. And this is where molecular products and decomposition happen. And this is true for particularly for low linear energy transfer radiation. So for electrons, this is what it should be. But here I have put this. There is a third pathway. So you excite your molecules. First you ionize, but then these recombine really quick to excited electronic states. These start going down to the single excited electronic states, and either you go back to your ground state, either you produce products or radiation products. So this is the one that would produce damage. This is why I was very interested to study this one. But there is a third pathway for this in high linear energy transfer radiation. So for X-ray, and this is what Sebile, he got the Nobel Prize. He did the ultra fast TM in Caltech. So he proposed this for the first time. And what there are evidences that for high linear energy transfer radiation, then you can have this pathway where the high excited energy electronic state can also produce damage. So and this is what we think that is happening, that the high energy excited states in the microscope, if you really have very high dose rates, and because we have this interaction when you are scanning your material, we are depopulating the single excited electronic states because you are producing damage with the high energy, damage. This energy is going somewhere else, so they carry chemistry. This is what we believe. And yeah, well, I know it's not the, well, okay, so conclusions of this. Yeah, we need like new ways to measure like what is going on if we want to solve some of the problems that we cannot solve just by lowering the dose or scanning different and all these things. So in order to have ideas, developing knowledge of what it is exactly that is happening could be important. And then we have used cryo-EELS to look at the oxygen KH that gives you access for water to many of the radiolysis products that you are producing. And also for looking at the excited electronic states in liquids and which, if you count the very high energy resolution, so even vibronic structure. And yes, it's what we believe from the experiment that we did is that these high energy states could be carrying chemistry. And then this another evidence together with the one that we have with the radiation chemistry that we are in conditions that are close to X-ray. So this interaction between sparse in the non-homogeneous because of the very high dose rates. Okay. We are done.
Did you do different tests between whether you like plunge froze vitreous ice or plunge froze the water to freeze it in the vitreous state versus cooling it more slowly so it crystallized in different ways and seeing if that changes the radiolysis outputs?
It does, yeah, it should change it, but no, it's just that, well, they have an stability, the cryo holders, so eventually it becomes crystalline at some point. So, but no, we have, yeah, no, I haven't been comparing because we try to make it vitrified every time. I try to like do always the same. Yes, so no, I got this question before because they did a paper on crystalline ice, Gindijureo with Andreas. Yeah, he has a paper on looking at crystalline ice. Yeah.
Any further questions? Okay, I think everyone is tired. Then let's thank Patricia again.
Mhm.